So, you get the volume fraction. Okay, now volume fraction is equal to mole fraction. So, actually we can easily prove that by using Amagat's law of partial volumes. When you use that, we can prove that the volume fraction is nothing but the mole fraction. Okay. So, for example, see, we can write like this. So, when you conduct an experiment in which, see, for example, P, you have P V equal to nRUT. Okay. So, now I make a constant pressure device. Assume that we have a frictionless piston acting on a cylinder and try to inject the mixture into this, so that it occupies a volume V and let the pressure be constant at P and temperature is T for the mixture. Okay. So, when you maintain the pressure as P and temperature as T, you will know what is the volume occupied by the mixture. So, this is RU. Okay. So, RU also is known to you. So, now this will be the equation which will be obeyed by the mixture when it occupies the volume V exerting a pressure P at a temperature T. Now, I remove this mixture and by the volumetric analysis, I know what are the volume fractions of individual gases. So, it will say that CO is this much, CO2 is this much, O2 is this much and so on. So, volume fractions of each and every component present in the mixture will be identified and we will know that. So, you know the components now, try to inject one of the component here. Now, while doing so, keep the same pressure. Okay, so, P is maintained same. Similarly, I will keep the temperature same, RU is also same. Okay. Now, this component 1 will occupy different volume for the same pressure and temperature. So, that means component 1 volume occupied by the component 1 is say V1. So, that means I can calculate N1, which is the number of moles of component 1. So, if you divide this, you will get V1 by V equal to N1 by N. So, that means V1 by V is what? Volume fraction of the first component, correct? So, V1 by V, I know that VF1, this is called V1 by V, I know this. So, now this is nothing but the mole fraction. I will say mole fraction of the first component X1, that is it. Okay. So, volume fraction is defined as the ratio of the volume of the given component to the volume of the mixture. So, now I have shown that volume fraction is equal to mole fraction. So, the volumetric analysis gives the volume fraction which is nothing but the mole fractions, and if you add all the mole fractions you will get 1. Okay. So, mole fraction, what is mole fraction? It is defined as the ratio of the number of moles of the given component. So, for example, here the first component, number of moles occupied by the first component is N1 divided by the number of moles occupied by the mixture is N. So, N1 by N is X1. Similarly, for any component, jth component, Xj is Nj by N, that is it. So, mole fractions are defined. So, previous slide we have defined mass fraction, which is nothing but M1 by M is the mass fraction of the first component and so on. Okay. Similarly, here by volumetric analysis, I have got volume fractions and we have proved that the volume fraction is nothing but the mole fraction. So, use that and get the mole fractions directly. This is nothing but what? This can be written as VFJ, volume fraction of the jth component, that is it. Okay. So, we have now quantified the mixture either in terms of mass or in terms of moles, volume fraction which is nothing but mole fraction. So, we know the when you subject the mixture to volumetric or gravimetric analysis, you get mole fractions and mass fractions. Okay, that is what we have got now. Okay, anyway, this identity we know that, just see that when you add all the mass fractions you will get 1 unity. Similarly, when you add all the mole fractions you will get 1 unity. So, like volumetric fractions, if you add you get 1. So, like this. So, now how will you calculate properties related to mixture once the components of the mixture are known? So, that for that we use what is called mixing laws. Okay. So, once mass fractions or mole fractions of the components of the mixture are known, then the properties of the mixture can be evaluated using mixing laws. So, first what I will try to do is try to calculate the molecular weight of the mixture. Okay. Molecular weight of the mixture can be calculated with these expressions. So, we can easily do this. For example, you know, for the mixture you can write like this. So, M mass of the mixture will be equal to m1 plus m2 plus and so on to mn, which is nothing but the mass, individual masses are summed up will give the mixture mass. Okay. Now see, molecular weight m is in kilogram per kilomole. So this means I can write this as the mass of the component divided by, or mass of the mixture divided by the number of moles of the mixture, kg per kilomole, correct. So now I will substitute mass, I write mass in terms of moles. So I will write this as n into m. M is, capital M is the molecular mass, small m is the mass of the mixture, mixture, yes, here. So here similarly write for this n1 m1 plus n2 m2 plus and so on to plus m n, sorry, okay. Now I want the molecular weight of the mixture, this is unknown. Now divide this equation by n. So you will get molecular weight of the mixture is nothing but n1 by n into m1 plus n2 by n into m2 plus and so on to n, capital N divided by n into m n. So that is what I have written here, sigma, this n1 by n is the mole fraction of individual components into their molecular weight. So xi, mi is nothing but, xi is nothing but the mole fraction of the component into its molecular weight, and I am summing up all this. So when I sum up the products of mole fraction of the component with its molecular weight and sum it up, then you get the mixture molecular weight. So that is what the proof for this equation is. So once I know, this is a mixing rule, this is a basic mixing rule by which weighted average of the molecular weights are taken based upon the mole fractions. Why I am taking here xi? Because this is per mole, kg per kilomole. So I am just equating this and writing like this. Okay, now you can ask, okay, one volumetric fractions are known, mole fractions are known, so I can do this. If I do the gravimetric analysis, so I only know the mass fractions now. So how will I calculate molecular weight? That I can start with this. If for example I can do this, now I can write this n equal to n1 plus n2 plus and so on like this, correct. Now you can write what I want to replace n by m. Now what is that? Then n equal to number of moles equal to mass by molecular mass. So this I can write as this divided by mass by molecular mass. Similarly for individual components, m1 by m1 plus m2 by m2 plus and so on plus mn by mn. Okay. Now divide by mass. So 1 by m will be equal to y1 by m1 plus y2 by m2 and so on. So that is 1 by m will be equal to y1 divided by m1 that is what I have written here. So m will be equal to 1 by sum of yi by mi, okay, yi by mi, okay. So that is what I have written here. So you can, first thing is you have to calculate the molecular weight of the mixture. Once you know the mole fractions or mass fractions, use one of these equations and write calculate that. Once you do that, the specific gas constant of the mixture is nothing but universal gas constant divided by the molecular mass of the mixture. So Ru by m, okay. So that is what we were saying that. So that is the first step you have to do, calculate this. So once you know this, then I can very easily write the equation of state as PV equal to n RUT, okay, or PV equal to m RT. Now you know R, so you can use this relationship. Okay, whatever way you want, you can use this relationship, and you have now got the value of R and the molecular weight of the mixture. Okay, now calorific equation of state, that is you want to find these specific heats. Okay, specific heat. Please understand that again the same weighted average can be used. Okay, now you have to select appropriate equations here. See, for example, when you want to calculate the specific heat of the mixture in mass basis, joule per kg Kelvin, okay, then you have to use mass fractions. So, for example, you know individual Cp values of every component in the mixture. Okay, Cpi is the ith component, the specific heat of the ith component at constant pressure, that into its mass fraction, Yi into Cpi. Then sum it up for all the species, you will get the Cp of the mixture. Correct? Similarly, Cv, you can do this. Or if you find the Cp of mixture, then R is known. So, Cp minus Cv equal to R, you can use that to find Cv and so on. So, this is done using mass fractions because I want a quantity which is mass specific per kg. So, I want to do this. On the other hand, if you have specific heats in molar basis, for example, Cp bar I want to calculate of the mixture, then I will use Xi Cp bar I. Okay, this Cp bar I is the molar specific heat at constant pressure of the ith species, that multiplied by the mole fraction and summed it up for all the species, you will get the Cp of the mixture in the molar basis. So, this unit is here kilomole, okay, instead of kg, kilomole. Or you can also do this, Cp into molecular weight, you will give this. So, Cp and Cv are related by molecular weight also. But if you have mole fractions and if you have the molar specific specific heats known, then you can straight away use this rule to find this. Mole fraction should be used when you have a molar specific quantities. Okay. So, now we want only such properties. Okay. Okay, now we will try to take a small example and try to see how we are going to go about the calculations of mass fractions and so on. Okay. One more thing is mass fraction and mole fraction are related, okay, like this. This is very simple to prove. Yi equal to Xi into molecular weight of the ith component divided by molecular weight of mixture. Okay, so you can very easily do this proof for this is, for example, I say M equal to, okay, this M is in kg equal to number of moles in kilomoles into kg per kilomole molecular weight. This is for the mixture. If I write for any component, say ith component Mi, we can write as Ni into Mi, capital M is the molecular mass. So, now you divide this, you will get Yi equal to Ni by N is Xi times Mi by M. So, that is the way you get this relationship between the mass fraction and the mole fraction. Okay. Now, let us consider a mixture, okay, products which is coming out of combustion of some fuel. So, basically this is typically when you combust methane with adequate air, okay, only what is required for combustion, full combustion, you get these products CO2 1 mole, 2 moles of H2O and 7.52 moles of N2. So, we will define why I get this later, but this is the products I have. It is at some temperature T and some pressure P. Okay. So, now when I write the mixture like this, I can read it as 1 mole of 1 kilomole, say like kg. When I say mass, I only use SI units kg. If I want to specifically say it is gram or milligram, etc., we have to specifically say that. So, normally mass is represented in kg in SI units. Similarly, the number of moles is represented by kilomoles. So, kmol. So, 1 kilomole of CO2 plus 2 kilomole of H2O plus 7.52 kilomole of N2. So, that is the number of moles of each component that should be so this equation is read like that. So, here the mole fraction of CO2 is calculated by, it has 1 mole and the total number of moles is 1 plus 2 plus 7.52. So, 1 divided by 1 plus 2 plus 7.52, the mole fraction of CO2 will be 0.09505. Okay. So, for example, nitrogen will have the highest mole fraction because its number of moles is 7.52 out of 1 plus 2 plus 7.52. Okay. Now, for this mixture, let us calculate enthalpy of the mixture. So, now you can also substitute everywhere. See, for this is the mixture, you can calculate mole fraction of each component like this. Similarly, once the mole fraction is known, I can calculate the, so how will you calculate molecular weight? You calculate mole fraction of CO2, mole fraction of H2O, mole fraction of N2, then use this equation, go back and use this equation, mole fractions are known. So, use this equation. So, molecular weight of this mixture will be here, molecular weight of this mixture will be equal to mole fraction of CO2 times molecular weight of CO2, that is 44, plus mole fraction of H2O times molecular weight of H2O is 18 plus mole fraction of N2 times molecular weight is 28. Okay. So, this is the way you calculate the molecular weight of the mixture. Then you can find from mole fraction you can find the mass fractions. If you, whenever you want that, you can find that. Okay. Then molecular weight of the mixture is known, so you can find R of the mixture as Ru divided by molecular weight. Okay. So, this mixture, let us calculate. So, now Cp, how will you calculate for this mixture? You have to know individual Cp values. So, for example, Cp of CO2 you should know, Cp of H2O you should know, and the Cp of N2 you should know, either mass basis or molar basis. Once you know that, then you substitute this in this equation. So, now you have calculated mole fractions, molecular weight of the mixture. So, mass fractions can be calculated. If you have Cp's in terms of mass basis, then you can use this equation here and substitute the Cp's of individual components. So, for this you can write, for example, here for this mixture you can write Cp as like this. So, if you have molar basis Cp, then you have to replace the mass fraction by the mole fraction and put a overhead bar to indicate that that is molar basis quantity, molar based quantity. So, this is the way you calculate all these properties. Now, let us go here and how will you calculate the enthalpy of the mixture? Enthalpy of the mixture is calculated by using what is called molar specific enthalpy. So, actually I can also put a overhead bar. So, since I specified clearly, I did not use that. So, H is the enthalpy of the mixture. It is nothing but sigma Ni into Hi. Okay. Now, this is, you have 1 mole of CO2. So, 1 into H of CO2 plus 2 moles of H2O, that is 2 into H of H2O plus 7.52 into H of N2. That is, these are molar based quantities. Okay. So, how will you calculate this? The molar base basically, how will you calculate this? This we will cover later. Okay. How will you calculate the enthalpy of individual species? I will let you know later. So, because this has some definition, standard enthalpy definitions, I will come to that when you do the heat calculations. Now, molar specific, see, that is what I have written here. Hi is the molar specific enthalpy of ith species in joule per kilomole. So, when you multiply by the number of species of each component, you will get the H in joules. Once you know H, see, normally we calculate H, then you recalculate the value of U using the definition of H, H equal to U plus PV. So, you calculate U as H minus PV. So, that is what we try to do here. So, now PV, use the equation of state. Okay. So, this is the way you calculate all the properties. So, this is about the ideal gas and ideal gas mixtures. So, in ideal gas, I will just quickly summarize. Ideal gas is it's a real gas which obeys a simple equation of state like this under specific conditions where its density is low, so that the intermolecular forces between the molecules are negligible and the volume occupied by the molecules are also negligible. Under these conditions, then you can see that the gases obey this equation of state. V is specific volume based on mass, PV equal to RT. R is the specific gas constant. So, this is the equation, and this equation can be written in several forms like P capital V equal to N RUT, or P capital V equal to M RT, R is the specific gas constant, and so on. Even P equal to rho RT, P equal to C RUT. Several ways you can write this equation, and this is a simple equation which is obeyed and relates P, V and T. Okay, this is possible only when ideal gas assumption is valid under certain ranges of temperature and pressure where the densities are low enough. Okay, now another thing is in calorific equations of states, one more simplification is possible, that the internal energy and enthalpy are functions of temperature only. That means you can write H as a polynomial of temperature, or U as a polynomial of temperature, and so on. And the advantage is the Cp and Cv are written as ordinary derivatives of the enthalpy and internal energy respectively. Okay, and Cp minus Cv will be equal to R. So, these are the fundamental equations which are obeyed by an ideal gas. And if I have a mixture, ideal gas mixture, each and every constituent of the mixture is an ideal gas. If so, the mixture also behaves like an ideal gas, that means obeying that same PVT relationship what we have shown before. The mixture, what are the constituents in the mixture is quantified by gravimetric or volumetric analysis. When you say gravimetric analysis, I can get the individual masses of each species M1, M2 to Mn, okay, and masses are directly got, and you know the total mass which is examined. So, you will get the mass fractions of all the mixtures. Mass fraction of a component is equal to mass of the component divided by the mass of the mixture. Okay, then by volumetric analysis you will get the volume fractions of each and every component, and we have just shown here that the volume fraction is nothing but the mole fraction. By the simple experiment, when you want to keep the pressure and temperature constant and see what is volume occupied by a particular gas mixture or individual gases, then you can show that the volume fraction is equal to the mole fraction, and in that case you can see that you can write the mole fraction as volume fraction Nj by N, that is the mole fraction of the jth component is nothing but number of moles occupied by the jth component divided by total number of moles, which is nothing but the volume fraction which we measured in volumetric analysis. Now, the identities, important identities are sigma yi equal to 1, sigma xi equal to 1. Okay, now once you know the components of the mixture, how will you get the properties of the mixture, other properties which are required for us? Use mixing laws. First and foremost property what we will try to evaluate is the molecular weight of the mixture, which is nothing but m equal to sigma xi into mi, that is mole fraction of an individual component multiplied by its own molecular weight summed up for all the species will give you the molecular weight of the mixture. Similarly, you can use the mass fractions. Mass fraction divided by its molecular weight and summed up, its reciprocal will be equal to the molecular mass of the mixture. So, once you know the molecular weight, I can calculate the specific gas constant of the mixture Ru by m. Okay. So I have just tried to derive these equations here, and coming to the specific heat of the mixture. So, first of all you have to know what the individual specific heat should be known to us. So, by measurements and a lot of correlations are available, tables are available, and we can take individual Cp values from those, and once you know that if it is mass based, so joule per kg Kelvin, then you have to use mass fractions and get the Cp of the mixture as sigma yi Cpi, and here Cp is in joule per kg Kelvin. But on the other hand, if you have molar basis, for example joule per kilomole Kelvin, okay, then mole fractions have to be used instead of mass fractions, and you get this Cp bar equal to sigma xi Cpi bar, where this overhead bar represents that it is molar based quantity. Now, if you get a mixture like this, say mixture has some moles, like any equation is actually written in terms of this type of number of moles only, standard practice. So, when you have a mixture like say 1 kilomole of CO2 plus 2 kilomoles of H2O and 7.52 kilomoles of N2, then you can calculate the total number of moles by summing up the number of moles in each component, and the mole fraction can be found by dividing the number of moles of individual component to the total number of moles. Like for example, for CO2 it is 1 by 1 plus 2 plus 7.52, okay, and so on. Once the mass fraction is known, mole fraction can be calculated, or otherwise if mole fraction is known, mass fraction can be calculated by using this equation, yi equal to xi times mi by m, where this mi is the individual molar mass divided by the molar mass of the mixture. Then this is the last one. So, the enthalpy of the mixture is calculated by just summing of enthalpy of the mixture is actually calculated using what is called molar specific enthalpies, which is in joule per kilomole, and multiply that molar specific enthalpy of individual species with its own number of moles. Okay, so Ni into Hi, and sum it of all the species, you will get the enthalpy of the mixture H in joules. Now, internal energy can be calculated using the definition of the enthalpy, H minus PV equal to U. So, that will be, then PV can be replaced by the equation of state. So, this is the way you calculate the properties of ideal gas mixtures.